All right. So it's a pleasure for me to introduce our speaker today, Jordan Goodman from the University of Maryland. Jordan is a, can I call you a figure in astroparticle physics for many years, and in high energy gamma ray astrophysics. He, in particular, has been one of the driving forces behind the establishment of the ground-based water Cherenkov technique that we're going to hear about today. Jordan got his PhD with Goran Yod, I believe it was,
yes.
Who is a graduate of our physics departments. That makes him a academic relative of ours. Grandson, academic grandson. And he has won several awards. He's a fellow of the APS and the AAAS. He's won a ridiculous list of teaching awards. I mean, it's half dozen or more. So he's really dedicated to his students. My favorite fact about Jordan is actually that he has held every academic position at the University of Maryland, from undergraduate to graduate to postdoc, assistant, associate, full professor, chairman of the department, now distinguished university professor, and I think just this week, chair of the university senate. So he's virtually run the table on that. And today he's going to tell us about some really exciting results that have come out from the latest experiment that he's working on, HAWC, of which he is the PI and spokesperson. So take it away, Jordan.
Well, thank you for inviting me. It's a pleasure to be here and see some of my old friends, and it's exciting to be able to tell you about HAWC and our first results. So I'll give you a little background of where we are in gamma ray astronomy, and I'll kind of go through the outline of the talk. So I'm going to start with gamma ray astronomy, and of course, the first thing you have to show is the TEVCAT slide that shows where all the sources are. That Scott is the keeper of TEVCAT, which is this picture here. But I'll tell you a little bit about gamma ray astronomy and why we do it, and cosmic rays, which many of you know all about, and ground-based arrays and air showers, and I have a couple cool videos that give you a different way of looking at the air shower. And then I'll tell you about HAWC, its design, its construction, its performance, and then I'll tell you about our new results. So we just first put out our first year's catalog, and we've seen a number of extended, we've seen new sources, we've seen other sources in a different way than people have looked at them before. We have some results on transients. Some are not as exciting as others, but we've been looking at transients, and we have limits on dark matter. And if I have some time, I'll tell you about the anisotropy that we saw with our first experiment, and I'm seeing again, and I had some very interesting discussions with Priscilla about today. So this is a HAWC collaboration. Okay, it's a U.S.-Mexico collaboration, so we are obliged to watch the World Cup when it was on in our collaboration to beat Maryland. So it's about half U.S., half Mexico. And it's a lot of people who were in Milagro and a lot of people who weren't in the Milagro experiment before. So gamma ray detectors, there are three sort of rough basic kinds of high energy gamma ray detectors for doing gamma ray astronomy. Satellites are an obvious first choice. Of satellites like the Fermi Gamma Ray Space Telescope. They are great for doing gamma rays. And the problem is a satellite is of order a square meter. And so when you want to get to high energies, you're limited by the fact that your detector is a square meter and it's kind of a meter deep. And so that sort of sets your scale for it. But it operates in a virtually background-free environment. And experiments like the Fermi Gamma Ray Space Telescope have given us an extraordinary view of the sky. And there are other experiments like also worked on here, VERITAS, which use imaging atmospheric Cherenkov telescopes, which are really wonderful at getting great angular resolution, have high sensitivity, and can explore with a fairly low threshold structures in the sky. In the middle sort of sit air shower detectors, which have some of the features of this, that they run 24 hours a day, 7 days a week with an open aperture looking at the whole sky. They're not pointed instruments. They have good sensitivity in the TeV, but they don't have quite the instantaneous resolution or sensitivity of the air shower, but they integrate over a long period of time. So they're good for looking at extended objects and wide field things. So sort of here are some of the pictures of the IACTs, including VERITAS here. and other experiments in the future CTA. And we see HAWC as complementary to these experiments, not really competitive. And that's sort of a change, because at first when funds were tight, we were competitive, and now we're understanding that we each have our own role in this and we fit in. So, as of last week, there were 176 known TeV sources, at least known to Scott, okay, in the sky, and many of them are supernova remnants and binary stars, and we've seen mostly the stuff that's on the galactic plane here. This is stuff in our galaxy. These are the supernova remnants and the pulsar wind nebula and the things like that. And then all of these things off the plane are other galaxies, HENs in particular, and more often than not, HENs that we're looking down the axis of, blazars. So this gives you some just overview picture of the sky. And one of the things that I want to say at least twice is that a lot of times we're going to talk about sources as if they're one thing. So we're going to say there's a Fermi source here, and HAWC sees a source there too. And we're going to say they're the same thing, but they're actually turns out to not be the same thing. They're associated objects, but often the lower energy source are seeing the pulsars, and we're seeing the stuff produced in the wind nebula around it. And so that's an important thing to realize, that they're connected but not the same. They're powered by the same thing, but not necessarily the same thing. So, what can you do with a wide field instrument? Well, a wide field instrument lets you do surveys really nicely for a gamma ray sky. You see the whole sky, overhead sky, every day. You can look, it doesn't matter if it's cloudy or rainy or it's light or dark. So you got to realize that half the sources in the sky cannot be seen by imaging Cherenkov telescopes for half the year because they're up during the day. Okay? And yes, you can think, well, what if it was the other? It doesn't matter. They're up during the day for everyone, if they're near the sun. Except we don't care with a wide field instrument. So we can discover new things, and we're particularly good at discovering extended objects, because we're not so keen to having a pointing, our angular resolution is good, but we look at the whole sky at one time. We can also study the high energy behavior, because we integrate for a long time. We have a large effective area. We get a lot of area on all the sources all the time. So we can extend our energy spectrum up to higher energies because of the length of time of our exposure. And because of some of these other things, we can study the morphology of sources. And we can even look for things like galactic diffuse emission and the Fermi bubbles, which we may or may not see, but we can look. We're also good at looking at transients, because we're looking at the whole sky every day. So if something goes flash in our field of view, we can see it. And so we can monitor HEN every day. We can also look for gamma ray bursts, which we should eventually, I will try to convince you, see, because they know that they will be high enough energy to be in our acceptance at this point. We can look for ice cube counterparts. We can look for LIGO counterparts, and we've actually already done this. And I'll tell you a little bit about that. And we can also do particle physics, which I'll talk less about, but we can look for dark matter by looking for annihilation in places where there is no light to look. So if there were a cluster of dark matter in a spot that was outside, nearby in our galaxy, but nobody knew there was emitted no light, we can still potentially see a signal from that because we don't have to point at it. So we can also look at some of the other things. Then we can talk about this weird anisotropy at the end. So just to give you a little preview, this is the Fermi lat high energy from 550 GeV to 2 TeV. This is their 6-year map of the sky of the Fermi lat. The HESS telescope in Namibia, this telescope here, produced a survey of the galactic center region for 10 years and produced this map of the sky. The reason it's small, this is aligned up in the scale. And then this is the HAWC 1 to 100 TeV, which we don't have very many 100 TeV photons, but this is above 1 TeV map for 1 year. So we're seeing the sources out here and over here, there, and we'll talk a little bit about that today. So this is the 1-year HAWC map. So just to put it in perspective with cosmic rays, because there's very old pictures, we've known about cosmic rays for 100 years, over 100 years. So 103 years ago, Victor Hess went up in this balloon, dressed actually like he's nicer than most people giving a talk, and looking very much like the Wizard of Oz balloon, and discovered that cosmic radiation, there was radiation coming from the Earth, but there was also radiation coming from the cosmos. And the main reason to show you this was actually, many of you have seen this picture, but this is a picture that I found someplace, which was great. Victor has going off on one of his balloon flights. And you know, they always say how graduate students are getting younger every year. I don't know. Looks pretty young to me there. Anyway, so this is the famous Simon Sporty did this plot, made this plot of the cosmic ray spectrum. And the thing that's amazing about this is, of course, is that we cover, we cover 11 orders of magnitude in energy and 32 orders of magnitude in flux. And it looks almost like a straight line. And we really don't have still a good clue about what produces the highest energy stuff. We really don't have a good clue about what produces this. But the cosmic rays give you a scale for why you need a big detector. Because just to say that the cosmic rays, which are much more plentiful than the gamma rays, at 10 to the 15th are particle per square meter per year. And so you're not going to get much in the way of a satellite measuring something smaller than this with a 1 square meter satellite. So if you want to get up here in this energy range to see where these things are pointing, you want a neutral messenger, and ground-based detectors give you this. If you look at the same spectrum but multiplied by E cubed, you see there really are features in it, and this is something which we've been trying to understand for a really long time. And gamma rays and neutrinos are ways to point back to these things because everything else bends in the magnetic field unless you get to Auger energies. So, basically, gamma rays and neutrinos can point to sources. Gamma rays have a sort of a more finite range than neutrinos, but they will let us at least study things that are relatively close by. So what's interesting is, and this is again a plot you can see from here, if you make this what's called the Hillis plot, which asks what sets the scale of the highest energy accelerators on Earth? Well, the answer is the maximum magnetic field you get and money. Right? Money tells you how big you can make it, and the maximum magnetic field is what you got. So you know that you get the LHC by taking the radius, and you have this simple formula that tells you if you plug in, momentum and B in Tesla and R in meters. So if you'd like to get to a, say, 10 to the 20th electron volt cosmic rays, all you need is to take this accelerator and put it here on this plot, which would make it, instead of being 27 kilometers or around Geneva, it would just have to stretch with a radius of 1 AU. Okay, so that's what that tells you, is that's the size of the containment area with a 2 Tesla magnet. 1 AU radius. Okay, so we're looking for either really dense high magnetic fields or more extended objects with larger areas. Okay, and this is a classic picture drawing of what goes on. What we know is that when you look at other galaxies, we know that there's other galaxies with supermassive black holes in them, that when you look down the line of this jet, what we see is the emission of very high energy gamma rays that would be too high in energy to exist in the environment they're produced in unless there's a large relativistic flow outward, though the Lorentz factor is in the rest frame that things can survive that dense area without producing pairs. And we also know from the time structure of these things, which vary on times of 10, 15 minutes, that you've got to be looking at some relativistically compressed thing. And we know that we see these shocks that are moving with relativistic factors of 1,000. So it's an interesting area to look. So this is one possible source of things that are interesting to look at. Here's an actual picture of one of these jets, okay, to give you some scale. There's 5,000 light years long, one of these jets. So they're quite impressive. Gamma ray bursts. If you look at the sky, this is our galaxy, and you look, the gamma ray bursts, which happen about twice a day in the universe, produce more gamma rays than the rest of the universe combined here at Earth. And so gamma ray bursts and the thing that's interesting is that they've been seen with energies up to 100 GeV. Okay, which is pretty amazing. Okay, because a lot of people argue that the ground-based detector would never have a chance to see a GRB because the highest energies, for a long time there was one 18 GeV event and people were a little fuzzy on that one. That was an egret. And they were like, well, maybe there is, maybe there isn't. But now Fermi sees them and they go up really, tremendously high energies. So we have a chance to look for these things with a ground-based detector. So again, the idea is, so the thing that limits, so there are lots of things that produce gamma rays. Okay, there are lots of things that potentially produce neutrinos. But so gamma rays can be produced. One of the things we're really trying to get to is what is the source of the cosmic ray hadrons? Because most of the cosmic rays we observe are hadronic, and because they're charged, we have trouble pointing them back. So one of the things we want to look for is gamma rays that come from pi zero decay. And so if you get gamma rays from pi zeros, you know that that was a hadronic source that started it. The other thing you can look for, what we mostly see, however, are synchrotron gamma rays that are produced by electrons and positrons. And one way to tell the difference between those is to get to high enough energies. Because above about 30 TeV, this mechanism starts to break down and is very inefficient. Where this mechanism continues. So if we can measure the high energy gamma ray flux pointed back to objects that are producing it, and we can see stuff above 30, 40 TeV, we can say this is where there's hadrons being produced. Unambiguously. Of course, if you see neutrinos coming, that's great too, but they're harder to deal with at these moderate energies. Okay, so let me pass on that. All right, back to an old drawing I have of an air shower. Just let me remind you about air shower. So air showers, typical hadronic air shower, you come in with a proton, you hit an air nucleus, you produce an inelastic collision that produces lots of pions, and these are all, and the charged pions have a choice of either decaying or interacting again. The pi zeros have an infinitesimally short lifetime, so they immediately decay into E plus into 2 photons, which then initiate an electromagnetic cascade. So if your pi zero here produces 2 photons, which then pair produce, and those pairs bremsstrawn, and you get an electromagnetic shower. And the fundamental difference between a hadronic induced shower and a gamma ray induced shower is that while this picture doesn't show it, both of these are dominantly electrons and photons at the surface of the Earth. But in the shower that's hadronic, there are more muons and they're clumpier. And so this is the thing we use to tell the difference between gamma ray produced showers and proton induced showers. So let me show you a simulation. This is a 2 TeV gamma ray. And each of these little electron, this is an electron. This is an actual blow-by-blow simulation. This is the height in the atmosphere. And what you see is the gamma ray shower is multiplying, it's increasing in number. Here we have 10 kilometers high. Notice it's very nice and symmetric. Okay? And it starts dying out. So this is now you're at about the height of HAWC, right about here. And as you get lower, it starts dissipating. That's what an electromagnetic shower looks like when you move down through the atmosphere. If we start with the same energy proton-induced shower, it's much more stochastic. So here it is. You'll see the yellow are the muons. The blue are still electrons and positrons. Okay? And what you see is the muons spreading out because they don't interact again. But every once in a while, there's another hadronic interaction, which produces another cloud of electrons and positrons. But there's a large transverse momentum. And so this thing spreads out and it's clumpier. And if you look, and here we still are, 13 kilometers up, we still have a lot of electrons and positrons, but they have a different spread, and they're not nearly as smooth. Plus, there are these muons everywhere. And so you can detect the muons. That's the signature that differentiates a gamma ray shower from a hadronic shower, is the clumpiness of the muons. Okay, so this shower sort of dies out by the time you get to there, but this is what you get. And so the idea for us was we originally built this experiment called Milagro. And it sort of stood for the Maryland, Irvine, Los Alamos Gamma Ray Observatory, but it also means miracle in Spanish, and we always kind of felt it was a miracle we ever had funded. And, but we built this in an existing pond above Los Alamos in the Jemez Mountains. And the pond was there originally to do geothermal work, and it was sort of being abandoned, and it was filled with really nasty and horrible, all kinds of arsenic and stuff in it. So we cleaned it out, and we put a cover on it, and we instrumented it, and what we did is each of these, so inside this pond, I'll show you the picture in a minute, we had lots of phototubes and lots of detectors, and each of these red dots here represented one of these things, this was actually literally cut away in the experiment to show you what it looked like. There was an outrigger tank. And so we had 175 of these. Inside what we had, this was the cover that you could blow up to service Milagro. Okay, and here is a picture inside which shows 2 layers of phototubes. They're held down by a grid on the bottom and they're floating up in the water. And these phototubes and the ones in the outriders make up most of what HAWC is made out of. Not phototubes like these phototubes. Okay? So you can see there's lower layer tubes down here, and then there's upper layer. These are under 1.5 meters of water. These are under 6 meters of water. And a little close up, they have little cones in there to keep light from coming up from below and hitting them. And the whole idea was simple, that the way you do an air shower is, the way you reconstruct an air shower is you just look at the timing of the arrival time, and the timing gives you the direction. So the shower comes in, and the advantage of the water is that since, and as the shower is dying out, a large number of its components are photons. But those photons, when they hit the water, will produce E plus E minus pairs, which produce Cherenkov light. So what we do is we detect the Cherenkov light in the water produced either by electrons or muons, or by photons that produce electrons and positrons. And so we use the arrival time to point back into space. What our simulations told us was that if you looked at a Monte Carlo, if you looked at the bottom layer of the Milagro pond, and you looked at the simulation, what you saw was the clumpy behavior from protons. And since 99.999% of our data was protons, you can just look at data and ask how does it compare to the Monte Carlo, and the data look a lot like the Monte Carlo. But it also, the Monte Carlo also shows that gamma rays would not look clumpy like this, that they would look smooth. And so we developed parameters to allow us to cut on smooth-looking showers. And what we're able to do is to make the first really wide field maps at TeV energy, actually about 10 TeV, of the sky by looking at these, by cutting on this thing and seeing lots of gamma rays. And what, again, this is the second place I'm going to say this, what we found is that these were largely associated with Fermi-detected pulsars. But they weren't necessarily the same thing, and not even necessarily centered on them, but they were just associated with them because we were seeing the nebula around them. So what we saw here, for example, so these white dots are the Fermi sources, okay, and this was our Milagro detection. So we took 8 years to do this. It took us a while to figure it out. We had to build outwards, we did all this, and so we ran Milagro, and then we decided that if we'd done, Milagro was defined by the pond we had, and the way we did it, we decided what we really needed to do was to go to higher altitude and have better isolation of our detectors. But we did some interesting science, and I think this is kind of an instructive thing. So one of the sources that we discovered, this 2019 plus 37, okay, which we first saw, the thing that made this difficult, the reason the Air Cherenkov telescopes who had looked in this regime before didn't see it is that it's a very hard spectrum source. The Air Cherenkov telescopes are sensitive to, or have a high sensitivity in the several hundred GeV regime. And you know, people talk about communication being important. One of the early parts of the tension in this field was a lack of communication. Because when we said we saw this thing, and we saw this thing, for us it was half the significance of the Crab Nebula. And the Cherenkov telescope said, we can see the Crab Nebula in a half an hour. We spent 5 hours on this, we don't see it. And you go, well, that's because it was half, but with the Crab Nebula has a fairly soft spectrum compared to this. So for us, for the Air Cherenkov telescopes, this was a few percent of the Crab, where for us it was 50% of the Crab, because they're different spectrum. And that message got a little lost. But what's interesting is the Milagro sort of said, well, our data is consistent with these points here. And then VERITAS went and spent a lot of time on it and measured it and found their data was here. But there was another ground-based experiment, Argo, which looked at it and said, oh, they were lower energy than us. So again, they had this problem because it was lower, it was a hard source. They said, we don't see it, and its spectrum has to be, it's not there. And by the way, these are our upper limits, which you can see really almost mirror the VERITAS data. So had they just assumed that we didn't make a 12 sigma error, they would have been almost able to measure the spectrum. So this is kind of nice. And what VERITAS has shown us, looking at some of these interesting sources, is that this is the VERITAS signal at, let me go back. This is the stuff below 1 TeV of this source. This is above a TeV, And the morphology of the source is not the same at low energies as it is at high energies. Because the place where the acceleration is taking place may well be different. And so one of the goals of a HAWC experiment is to work with VERITAS and work with other IACTs to map out over a much more extended range what the morphology of these sources is, to try to understand the acceleration mechanism for the gamma rays. Another thing Milagro discovered, which I shall mention, is this weird anisotropy of the cosmic rays. These are not gamma rays, these are cosmic rays that showed an anisotropy at the 0.1% level that was completely unexpected, but has now been observed by lots of other experiments, and maybe I'll talk about that at the end. Okay, so what do we want to do? We want to go to higher altitude. We wanted to go to individual tanks that didn't have, that had optical isolation. So HAWC stood for the High Altitude Water Cherenkov detector. And one of the main ideas is that HAWC wins by having a much larger deep area where you could do gamma hadron separation. And the easiest way to kind of see this is that if this was a gamma ray shower of 20 GeV hitting the ground, okay, deposited on the ground, this is the energy distribution ground level, what you see is you might see, this is a proton. Protons are clumpy, gamma rays are not. If you're looking for a clump, the size of the Milagro pond was this. You couldn't see there was multiple clumps. The size of HAWC, you could definitely see multiple clumps. So if you ask, what's the probability that I got one extra clump from a muon, it doesn't go linearly, it goes exponentially in your ability to reject background. Because all you'd have to do is say, what are the odds that I get at least one extra muon? One muon. Okay, and if I get 3 muons, I just crush it. So that was the idea behind HAWC. So why did we go to Mexico? Well, we wanted at a high altitude, and we had water. And so we prefer it didn't freeze. So that kind of pushes you down toward the equator. The galactic center was toward the equator. And we wanted a place that, and you know, nice, I mean, there are a lot of nice things about it. It's in Central Time, so it's easy to work on. You know, we looked at Tibet, we looked at Mount Chacaltay in Bolivia, but this site clearly offered us things. It also offered us the fact that there was local infrastructure nearby. So where this picture is taken from is where there's this large millimeter telescope there. And the large millimeter telescope had power lines running up the road, it had Ethernet fiber running up the road. And so it allowed us to build by only extending the utilities a kilometer to get to the site. And so where it is this is Mexico City. Here is Puebla. And we're about an hour and a half east of Puebla, near the Pico de Orizaba, which is the 3rd highest peak on the continent of North America. We're at about, this is about 18,000 feet. We're at about a little under 14,000 feet here. And it's an experience working 14,000 feet, especially if you're a sea level person. The people who come from Los Alamos don't have as much trouble because they already live at 8,000 feet. Mexico City is the same way, you know. But those of us from sea level, when I show up at the site, my blood oxygen level is often about 80%, which doesn't necessarily make you feel bad, but it makes you stupid. So when you think to yourself, you get there and you think, I think I should change the high voltage. Always text somebody who's at sea level and ask. You get a different answer. So here we are. So here's HAWC. It consists of 300 of these large water tanks, okay, and they're densely packed. There's a counting house in the middle, there's a utility building over here, and the idea is that HAWC would have a sensitivity which, integrated over either 1 or 3 or 5 years, would have a sensitivity better than either HESS or VERITAS that's spending 50 hours on a source. And we would have this over the entire sky in our field of view. It turns out that now we've been taking data, okay, and this was what we put in our proposal, and we're taking data. We aren't doing quite as well down here just yet as we thought we would, but we're doing much better up here, so this is not real, but it's kind of an estimate of where we are. But it looks like we're probably a little bit, maybe a factor of 2-ish, a little bit around below a TeV, below where we expect to be in sensitivity, but our sensitivity at higher energies is much better. And the reason that it's not that our Monte Carlo was wrong is we didn't have the nerve to say this in our proposal, because we couldn't find protons that passed our gamma cut. but you can't say it's perfect. I mean, that's one way to get a proposal rejected. Our Gamma hadron rejection is perfect, no. So we started to cut it off where we had 5 events that passed, which said, well, we said it's going to be better than this, and it turns out it's better than that. So it's really working well. One of the things we're excited about being able to do is to see gamma ray bursts. The reason we're confident we can see gamma ray bursts is they're high enough energy that with our acceptance, if one occurs within sort of 20, 30 degrees of the zenith of one of the high energy ones, like have been seen by Fermi, we will see it. Because in this event, which was not necessarily one of the brightest, but one of the brightest, not the brightest event they saw, this is what you saw in the Fermi Gamma Ray Telescope. This is the highest energy events. This is all of the LAT data. This is the GBM data. And what you see is this burst, which was a couple seconds long. It may have had a precursor in low energies. We don't know if it had a precursor in high energies. We really don't know what the high energy behavior above a GeV looks like. If this had been in the HAWC field of view, it would have looked like, we would have seen this. So we would have been able to measure it really, really well. And so we would observe hundreds of events, and that's assuming that the spectrum only went to 30 GeV. If it went up to as high as some of the other ones, we're just going to get blasted with it. So we're waiting, we're anticipating, but we don't have any yet. So just to give you some comparison, HAWC is about 15 times more sensitive than Milagro. And what that 15 times means is, it's 15 times the signal to the square root of the background. So it took us months to see, like the Crab Nebula, it took us 6 months to see, 5 sigma. We see it in a day. Because it's 225 times faster to get that signal over the square root background. So that's a huge thing, to be able to see, the signal in a day. And what's interesting is, Fermi, if you looked at this plot pictures, I didn't really show you in detail, of where the Fermi sources were and what we detected, they were about 50, if you looked at the number of sigma they got and the number of time they ran, Fermi is about 15 times more sensitive in the GeV than Milagro was in the TeV. HAWC is going to be about the same sensitivity as Fermi, but in the TeV. So almost 1,000 times higher energy, which is exciting. So, for galactic source. So, this is a sketch of the tank. It's 5 meters high. It's made out of the outer part of the tank is made of corrugated aluminum that one person can carry, and you make this, and you have a bladder inside that's filled up here. So the original time the person who made this drawing was made out of Wisconsin. Discovered that the person was only this tall. And we discovered, no, that's not a 1 meter, we don't have 1 meter people. And then they discovered, so the other day they were complaining about this, and so they discovered that this is actually a better scale, right? It's really a T-Rex scale. It's about 5 meters high, okay? And it's built from the ground up. So you build it top down. It's kind of a weird thought. So we build the top layer, and then we jack it up. Let me show you how we build the tank. And it's in Mexico, so there's a lot of hand labor here. Okay, so forget that part. What we're going to do is first dig a trench. It's 60 centimeters deep, and then we put these jacks in place, and then we assemble the first layer and put the roof on it, and then we jack it up, and put the second, third, and then eventually lower it back down and fill it in, and you have a tank. And then you put the bladder in through a hole in the side, and you blow it up with air, and then you fill it up with water. Now, why this is important is we've had a problem recently, and I want you to think about this construction technique. When you see the problem we've had, you'll understand why the problem exists, because of the way we built it in the first place. And it was a good idea, it just doesn't make servicing very easy. Okay, so the phototubes go in when the thing's wet. So what you have is at the bottom this kind of cool little gizmo that captures this ball on the bottom of the phototube, and all you do is you pull them in on strings, and you can latch them into place at the bottom of a pre-surveyed location, and then you can pull on them and they pop back out, and you pull them up on a string, and you can service them if you need to service them. So you never go in this tank. The water's deep and cold and dark, okay, and you only deal with a hatch on the top. And so here's our little mechanism, and that works really well. We even had to deal with the fact that occasionally a string would break, and our engineers came up with a way of firing a new string through the hole with a magnet, and it's pretty cool. Anyway, it works. And again, the idea is simply, same idea as with Milagro. The shower plane comes in, we get this thing, the shower front comes down, hits the detector, And by doing the timing, we can reconstruct the direction. So here's a slowed down real event. You can see the arrival time of the shower across the thing where the color is the log of the charge, and you can see the arrival time in some thing to give you some sense of how a shower moves across the face of the detector. So we started building, the nice thing about building a modular detector is you don't have to wait for it to be finished to start running it. So when we first had the first 30 detectors, we started operating the experiment. And so we started learning about what it took to run the experiment, and then we expanded to 111 counters. And then we operated that beginning in August 2013 as HAWC 111, and then eventually we had up through November 2014, we had a 250 detector array, and like most things, the NSF, we asked for 300 and they say, that's great, we'll give you 250. But if you have money left over, you can build the remaining 50. So, but fortunately the Mexicans didn't talk to the NSF, so they gave us the money for the 300, and then we had enough, and so it all worked out. So we built all 300. Okay, it just took a little while. So we eventually did that. So we inaugurated this. This picture was taken on during the inauguration, so the people at the tent here, on the 20th of March 2015, a year ago. Okay, this was taken from a drone. Okay, so we've been running. So it took 13 tanker trucks full of water to fill each tank. So that turns out to be 3,900 tanker truck trips to fill up the array, driving up the mountain road. And we spent about $200,000 in just changing the potential energy of the water from where it came from. Okay, so that gives you some scale for it. It does snow there occasionally. So this is sort of the construction video. It took 4 years to build the entire thing, and the camera up there moves from time to time, so it's a little bit jumpy. But this sort of gives you a sense of the stops and starts. And a lot of this had to do with importing stuff into Mexico, getting funding. Mexican funding is done different than U.S. funding. U.S. funding is done different from any rational scheme of its own. So money comes in spurts and things, and getting stuff into Mexico, and issues. But we got it all. It took it a little while. You can see the shadows. There was times when we stopped because of, again, import-export issues and things. But eventually we got the last two. This is the 250 part of the array built here, and then we came back and built the last 50, which we had space for here. And that's kind of it. So that's building it. This is a drone video of what it looks like at, just before the inauguration. So you can see the countryside. It's just a magnificently beautiful place. Okay, the LMT is up this hill over here, and you look down and you can see we have one of the old Hegrid telescopes here, which we have yet to utilize fully. This is our water filtration plant. This is the Pico de Orizaba up here. This is the lava flow from the time of Cortez, which heralded the arrival of the Spanish. But you get some sense of what the array looks like from there. So our Monte Carlo for this told us that gamma ray showers would look like this, hadronic showers would look like this, and the dominant difference between these would be large energy depositions away from the core. So this is what we went to do. This is what the data actually looks like. So this is data, just a random spot in the sky, which is certainly a hadron. And this is a likely shower from the Crab Nebula. So that's what the actual data looks like. Okay, so you can see here there's high energy stuff away from the core. And that was kind of our first cut. And what you can see here, we now have a gamma hadron parameter we call pinkness. So this is regions surrounding the Crab Nebula, and this is the data with the crab bin. And what you see is that in this, there's, like the background, but there's this excess of data here, which are the gamma rays. So we see, we can make a cut, which gives us the best signal to noise rate, signal to square root of background, which is like here. But we can also make a cut out here, which has virtually no background. And that actually turned out to be critically important to building the array. Because being able to have a pure sample of gamma rays to sort of calibrate on turned out to be really important. And by the way, if you look at the lateral distribution, hadronic events have all this stuff. Gamma ray events look just like the NKG distribution of old. And so here's a little movie with some gamma ray events. You can sort of see they're spread out, but they're smooth. There's nothing big and clumpy about them. They kind of have nice characteristics, and these are gamma ray events, but I'll slide past this. So one of the things we discovered that our angular resolution wasn't quite as good as we expected it to be. It seemed to be at the highest energies off by about a factor of 2. Not quite, but almost. And we tried to figure out what it was. We puzzled over. But one of the ideas that we pushed forward was, I said, look, you've got gamma rays. Why don't you just take a pure sample, which was, we found a sample that was 10-to-1 signal to background, and ask why aren't they pointing exactly in the right location? And one of the guys at Penn State was able, one of the things he ran, showers are not planes. We know this. They have a curvature to them. And we had, from our Monte Carlo, determined what that curvature would be. But the Monte Carlo was not exactly what you'd say definitive. If you went 1.5 sigma off from what it said, you could have a different parameter to define that curvature. And if you looked at it, what you could see was the point spread function, just look at the blue here for a minute, depended dramatically. We were here at 0, which was the one we were using before. If you adjusted downward the curvature direction, made it a little flatter, you went from an angular resolution which was 0.2 to 0.12. So we were able to tune this, and we went from this kind of picture to this kind of picture, but more importantly, we went from 44 sigma in the sample to 80 sigma on the crab by making this one adjustment. And so then it was down, it was matching our projected angular resolution. So this is what our point spread function looks like in theta squared, which is how the IACTs like to point it. And this is kind of, if you look at it as a function of our bin number, which is our energy going up, we get down to about 0.18 degrees or something, which is about twice the angular resolution of an IACT. Twice worse, but still, it's an all-sky instrument. And Milagro at the same energy was about 0.5 degrees. So much better. So this allows us to now get our first survey of the sky. So we have a year's worth of data. We reprocessed it using this right curvature fitting. We went through, this is actually 341 days, and we were able to make this map of the sky. Here's the constellations. This was shown at the APS meeting. And if you look at it in galactic coordinates, what you see is, we see, it's a little hard to see, there are 2 extragalactic objects we see quite clearly. We see all these sources along the galactic plane, and we see the Crab Nebula, and I'll talk about this thing out here, which is actually still in the galaxy. And so here they are. You kind of see, it's a little hard to see in this projection mark here in 421, but we have, in Milagro, in 1 year of data, we've sort of seen things at 5 times the significance we saw them with 8 years of Milagro. And much better point spread function. And so, if you look, this was 8 years of Milagro. Now Milagro was a little further north, which on this plot's this way. So so these are pretty high latitude sources for us, but we see them at fairly strongly. But this gives you an idea what the Milagro sky map looked like. This was our first pass with HAWC 111 data, and then this is what we've got in this current pass of data right here. So we've got a really nice view of the sky. We can again see things with very high significance. Our point source is Markarian 421, 501, and then the Crab. These are our benchmarks. And in our first year, if we look at the sources, we've seen about 40 sources in the first year, 25% of which are new. Now, the goal of HAWC, everybody likes to discover new sources. That's exciting. But one of the things we've discovered is not just new sources, but new characteristics of old sources. So, for example, this was a source, J1930 plus 188, that was seen by VERITAS. Okay, it was seen by Milagro, it was seen by VERITAS, but they saw one spot here. We're really seeing something that's kind of 2 or 3 spots. I'll say why. It looks like it's obviously 3 spots, but it may or may not be. I'll tell you that in a second, a little more detail. But yeah, this is the kind of morphologies we're now able to study by looking at extended objects and new things. So this thing is a supernova remnant, very energetic pulsar. It's about 8 kiloparsecs away. Okay, and this thing here, so we just try to develop, when we look at this, we go, how do we know what's one source and two sources and three sources? So we developed a criteria. The criteria was just a test which said, if there was at least a 2 sigma dip between here and here, we could say they were distinguishable. Well, it turns out in this picture, there isn't 2 sigma between here and here. There's 1.8 sigma between here and here. So by our own criteria, we decided not to call it, we called it another spot, but we said it might be well associated with this. On the other hand, this all could be one thing. It's a little hard to tell yet, so we're just working that out. So here, what we did is when we labeled this, we put our results out, we said, okay, this was, this in our HAWC catalog, the same thing as seen here by VERITAS and others. This is also, we called it distinct and gave it a new name and a new number. This one we gave it a name, but we put an asterisk next to it saying it might be spatially connected to that one. To tell the honest truth, when we put more data in, which I don't have to show you because it hasn't been proved, this actually looks like it might be spatially connected to this one and not that. The criteria is not a good one. We have to come up with a better method, but we're just developing it. But we're starting to see things that look like this, and by exploring this region with VERITAS and with other IACTs, we're going to be able to learn where the high energy behavior comes from, which is not necessarily the same as the low energy behavior. So we're trying to understand what these things are. We're studying morphology. I'll go through this rather quickly here. Here's some other spots in the sky which have been seen before. Here was that 2019 plus 37. This is where it was seen before. This is what we're seeing now, a slightly extended object. This is the Milagro contours. Milagro just saw one big sort of blob at 6, that's 8, 5, and 3 sigma, and this is 16 sigma, 15 sigma right there in the middle. So we're exploring these things, and what we want to do, we've got lots of different objects. We want to try to understand, the physics is to try to work to understand the spectra, understand why things are being produced from this pulsar wind in different energies and different wavelengths. Okay, so let me just, that's all this is saying. So the crab, one of the interesting things is, again, we can see a high signal to noise ratio. This is what that signal to noise, our weighted plot is for the crab. And this is an event that we saw that, depending on what you do, looks like it's clearly looked over 50 TeV. So this is the highest single identified gamma ray we have to date from the crab, which is just over 50 TeV, which is, out here on the plot. So this is high. So one of the most interesting things that we discovered with Milagro, which a lot of people thought was kind of tenuous, but it was really interesting, was there's this object Gaminga. Gaminga is one of the brightest GeV sources in the sky, in the northern sky. And it had never been seen with TeV telescope. Milagro saw this. And what we said was, if this is one object, we should take a big bin. And while this was all of this was kind of 4-ish sigma, when we made a big bin, we got to about 7 sigma. And changing one parameter, how you come up, we shouldn't be able to take you from those probabilities. So we argued that this was an extended object. Okay, and X-rays don't show. In the X-ray data, they see this, but this is that spot right there. Not this. So the pulsar, the Gaminga, where it came from, is probably there, but this was particularly notoriously bad to look at with a standard IACT. Because the way an IACT looked at stuff is, they would point the telescope there and get the background from there. So a source this wide and this big just automatically defeated the standard. And so they're developing new analysis techniques to look at it, but that was with Milagro. With HAWC, again, the point-like structure, a little different, at a little lower energy than Milagro, but still, we see the same extended object. And we see the same kind of, roughly the same intensity we saw with Milagro. And this thing, you have to realize, is several degrees across. It's a pulsar that's 200,000 years old. It's about 150 parsecs from here. And it's not that it's bigger than most things, it's closer than most things. So it's gigantic when you look at the sky. What was brilliant, and one of the things that people have argued, is that things like this kind of object could be the source of the positron excess that's been seen in AMS, because it's a close by, old pulsar that could be evolving electrons and positrons in our direction. What's interesting in HAWC is, this is, again, the HAWC map. This is the crab saturated out, 80 sigma. What we see is, again, Domingo, which we've labeled by our algorithm here as 3 separate sources, but it's really one big thing, we believe. We've also seen this thing, which, again, when you do a top-hat bin analysis, gives you a very significant, but not compelling, argument that there's a large signal, there's another large object, and the center of this is the center of the monogem ring pulsar. So it's characteristically very similar to Domingo, and it looks like we're starting to see a characteristic of these things. The reason you can argue all this is one thing is there's not much else around it. In the galactic, these are the galactic anti-center. In the galactic center, there's so much stuff you can't tell. But it looks like these are isolated objects. So I don't have time, I'll try to spare you. What we're trying to do is answer the question carefully. Can we map the electrons out? So, let me tell you about transient data. The crab has been seen to flare at GeV energy. Surprised everybody dramatically, but Fermi saw this flare, which was very significant. Argo argued they had seen a flare at TV energies, but no one else had seen it. We've been monitoring it for a year now, and the crab is completely statistically flat. We look at it every day. With the highest significance anybody's looked at, it's flat. On the other hand, when we look at the AGN, we've seen things that are clearly not flat. And so we've seen behaviors which are consistent with what other people have seen with flaring objects. As a matter of fact, we're able to monitor. We've recently put out our first ATEL, our first flare ATEL, where we saw that so this was just a month ago. Here was Markarian 501, excuse me, on the 5th of April. Here it is on the 6th of April. Here it is on the 7th of April. Here it is on the 8th of April. So you can really nicely see these flares, and we can observe it, and we are going to monitor all these sources every day. So we have MOUs with all the people in the field at this point. So we have MOUs with satellites, with the IACTs, with the network of things with IceCube, with Antares, and with LIGO. And the idea being that we will share data even before we publish it with these people, these different collaborations, to try to come together to increase our understanding of the field. So although we have not published these first results, we present them with the APS this evening, the one I'm showing you, we sent a much more detailed version of it to our VERITAS and HESS and MAGIC collaborators, on the MOUs, so they can start to study them in more detail. And we're working out final spectra and publication. So what we've done is, again, we've given this thing to our MOU. We're following up on observations by ACTs, and we've sent out this stuff, and we've produced a couple of ATELs, including an IceCube follow-up. And the idea is that if you looked at this, IceCube saw this event, which deposited 2.6 PeV in the detector. Its likely energy, it's a muon, its likely energy was 8 PeV, is this Monte Carlo energy. Because it interacted outside the detector, it went through the detector and went out the back end. And so if you simulate that and you put it together, it's something clearly more than what was deposited in it. Now, HAWC 111 wasn't pointing in that spot in the sky, but what we can do is we can go back and say, what was there the day before? What was there the day after? We weren't looking at, we were different sides of the Earth, but we did that. And so we can make passes 2.5, 2 days, 5 days, and do that, and we can, there was nothing there. Maybe not surprising, but we can, and right now we're starting to get more and more data in time with these experiments. So we've looked at GRBs, we've been able to set some limits on GRBs, and today there was a high energy GRB kind of out of our field, but we put out a non-observation. Unfortunately, we wouldn't really expect to. It was really a large zenith angle, but we put this ATEL out about 3 hours ago. Okay, so we can look in theory for dark matter the way everybody looks for dark matter. We look through annihilation and the gamma rays. And the idea is that if you look for example, dwarf galaxies which seem to have a high matter to light ratio, you can look for this. The advantage HAWC has is that it can look for things that have a 0 light to mass ratio. Okay, so you don't even have to know where to look. And so we can look and we can combine things, and we're starting to do this, and I'm sort of wrapping up. So we can look even if the visual luminosity is 0, and we have this view of the sky where we can look at all these different potential dark matter sources and stack them together. our current results are producing, like everybody else, limits, otherwise this talk would have ignored all of the stuff described in Discovery Dark Matter. Okay, so you kind of knew that was coming. So let me pass on that. And let me just sort of wrap up a little bit. I'll pass on the anisotropy, which is interesting, and just sort of conclude by saying that one of the things we want to do to get to higher energies is we need, like with Milagro, we need an outrigger array. And the purpose of the outrigger array is for high energy showers. We want a larger area, and all we need to know is where the core is. Once we know where the core is, we can reconstruct the direction really well because of that curvature issue. So what we're doing is, these are the HAWC tanks. We're putting these things out, which are more people-sized tanks. One phototube each, and we're going to spread them out all over the ground. So we're going to put 350 of them, and this was funded mostly by Los Alamos and Mexico. So we can go back to the NSF. So we're putting one of the same phototubes in here, and we're going to say to do this. The thing that's kind of interesting is the reason HAWC was 1,200 phototubes is we had 1,200 channels left over from Milagro electronics. Okay, and people kept saying, why didn't you use newer electronics? And it's one of those things of, of better being the enemy of good. And had we done that, we would have had a better experiment they wouldn't have funded. So we could build Milagro fast and HAWC fast and cheap because we used Milagro electronics. But the next channel was going to cost us a lot of money because we had to redo the electronics. But fortunately, this is where our collaboration in the field comes in. The electronics that's going to be used to do these outriggers is basically the flash ADCs for CTA. And Max Planck Institute is providing those. So we're now going to, and eventually maybe we'll propagate that back into the experiment if those are good ways to do it. So this is what we're up to with this. We have had some problems. Actually, we were down for 2 weeks till last Friday with a transformer explosion. So one of our transformers was lightning, and the transformer blew up, and in Mexico they don't stock them. So somebody had to build a new one for us, and it took 2 weeks, but we were back up and running. But we had a more major problem that turned out to not affect the operation of the experiment, but it's still a problem, is on January 13th and 14th, we had 28 inches of snow at the site, which is historic, and then it rained. And it put a tremendous weight on a lot of the roofs. Now these roofs are just there to protect the bladders. So they're not, technically part of the detector, they just protect the bladders. And what happened was that we crushed some of the ribs, but they're still protecting the bladders. So we realized we had to deal with this. The problem was, you saw how we built these things. We built the roofs on the ground and raised them up. And you can't just easily go in here with a crane and pluck them off because there's not space between them. So, and by the way, this is one of those interesting stories. We went to the NSF, we told we had our JOG, our joint operations meeting with the NSF and the DOE in Mexico, and this was just a week, it happened a week after this disaster, and we thought of it and we said, we think we can cover the cost within our operations. So at that point the NSF says, this is fine, we don't care. As long as we don't pay for it, it's great. But actually it turned out something weirder than that happened. The lab, Inouye, which runs the site, for some bizarre reason has insurance. And the insurance is going to pay for it. So eventually the cost to fix it is going to be zero. But we still don't know how to fix it. So that was a problem. But, this is what's fun about experimental physics is, you think everybody's sort of looking at each other and going, well, if you could walk on the water, that would work. So there are two things we came up with. One is for the outside ones, which a few of the water storage, we could use a cherry picker and actually pull the whole thing off at one time. But that doesn't work in the dense region. So what we found were these floating docks that are inflated. And you blow them up to about 15 psi gauge, and it's like walking on a hard floor. And they sit on top of the bladder and provide a perfect platform that a person can work from to reassemble the structures. And they fit right in between the ribs. And so, so it's one of those things. I know the University ground is about to have an NSF audit, and I know someone's going to want to know why we ordered floating docks. But, that's what you're there for. Anyway, so we're in the process of fixing this up now, but it hasn't affected, you don't even have to turn the detector off to work on it. Now, you don't even turn the tank off to work on it, because you're still outside the light tight area, it's all fine. And it's going to take us a little while, but we're repairing it. So that's what we're up to there. So let me just kind of finish by saying that we began full large-scale operations. We have a new experiment that's continuously monitoring, giving us a new view of the TeV sky and wide field. That we put out, our first year catalog is coming out. We've already shared with our MOU partners. We're going to have some diverse science results, and we're upgrading to get a higher effective area above 10 TeV. And one thing that's kind of cool about the thing is, if you go to Webcams de Mexico, there's a live webcam shot of the experiment, updated every 20 seconds. And sometimes you see really weird stuff when you look at a camera, like this. Okay, so it snowed on top of the mountain, and you can see the thing. But if you go to the Pico de Orizaba and you look at the live webcam view, it's usually working, and you can see the experiment kind of from this vantage point. So here we are, here's the Pico de Orizaba, here's the snowstorm. So thank you for your attention.
Time for some questions.
Yeah.
So, for point sources at least, sharper for ESF, what in the design of the experiment really sets ESF as a function?
The amount of detection, it's simply the amount of light you get. Okay, so the reason this is better is it's higher up with more tubes at deeper depth. So by going higher up, we get many more shower particles, and that's part of the reason we get a better angular resolution. Okay, and so basically, the more light you get, the better, the sharper the timing, and the more samples you get, the more samples you get. So you root end down, and that's what sets the.
Spreading the tank set doesn't make a difference because ultimately it's measuring the tilt of that.
Yeah, but the further apart you make them, it's the shower size that sets the scale that you want them dense. So for higher energy showers, you could in theory do better, but you'll probably run into systematics. Okay, so one of the things, we actually still run cable. And physical RG59 cable, which has dispersion. So if you start running really long distances, the new stuff won't have that. So, but yeah, that's what sets the scale. It's pretty much just the number of particles.
I'm surprised by the fact that you said you could see GRBs because it's only 30 GeV for a few seconds, and it's not a high altitude and you can't integrate on them. So
no, we don't have. So the point, and let me explain how an experiment like ours can see something at 30 GeV. Okay, you're asking a good question. So first off, you have to realize that the reason we can see stuff. So people say, "What is your threshold?" Which is actually a reasonable question to ask an IACT. It's not quite a reasonable question to ask a ground-based detector. The reason it's not reasonable is that what dominates what we see are when showers fluctuate further down in the atmosphere. So our effective area, which is sort of the area times the efficiency, is really crappy at 100 GeV. Our efficiency is 1% at 100 GeV. But it's 1% of 20,000 square meters. So it's 200 square meters. So you compare that to Fermi, which is a square meter order, and you can see at 100 GeV, we're 200 times the effective area. So, and our background, if you look at a spot in the sky, the background isn't very high in a second. So what you gain is you know what second, you know what time to look, you know where to look, so you don't have to integrate for a long time, and your sensitivity doesn't decrease. For a short time, your sensitivity is better if you get all the photons at one time because you don't have any background. So what we know is that even with 30 GeV, we should get clobbered, and so one of the things we'll be able to do, one of the problems is, you'd like to say we'll measure the energy spectrum. But we will, but only in the most binary sort of way, which is that a 30 GeV shower looks like a 100 GeV shower looks like a 200 GeV shower. But if you know what the spectrum looks like from Fermi, just doing the integral above a certain amount will tell you. And what's nice about HAWC is that our area times efficiency is almost flat to a TeV with an e to the -2 spectrum. So the fact is our acceptance rises like E squared. So if the spectrum is falling with us, we'll get the same number at 50 GeV as we get 100 GeV as we get at 300 GeV until they run out. Okay, because our area keeps growing with our efficiency. That make sense?
Other questions?
Peter?
How do you quantify the ejection for DC source, the equivalent particle shower ejection that you need or that you get?
Well, the way we quantify it is simply to look at the background near it and say, if I make this cut, first my Monte Carlo tells me what fraction of gamma rays I'm rejecting. So typically, the best cut optimally rejects about 50% of your gamma rays. Okay, and rejects about 10 to the 4th to 1 of your background. So, and that's a function of energy. So at high energies, what we know is that the back is you make a map and you see that virtually nothing survives in the sky, but there's this glowing spot of gamma rays. So it's pretty easy to know what your rejection factor is by how hard you've cut everything else. All right, and then you look at the source and you can estimate how many of those you cut, and then you can look at the softening of it too. But basically, we've done this through Monte Carlo, and the Monte Carlos pretty well predict what we're seeing. So, you know, it's kind of, I mean, on the other hand, what we couldn't what I was saying before is, the Monte Carlo, if you make a hard cut, nothing passes. We can't generate enough events to pass anything. So we have to kind of get that from the data, but you can get it directly from the data. And that's where we get it from. So that's how we know how we're doing.
Yes. So, Jordan, I wanted to ask, the future of the ICTA, CTA. What is the future of, undetected or LIGO, adaptive?
Okay.
Is it still?
So CTA has sort of talked to us about potentially building one of these things at the same latitude. Doesn't have to be the same place, at the same latitude as CTA. Okay, and moreover on the same longitude is what you do. So you don't need to be exactly latitude, just on the same longitude line, so you see the sky at the same time. Because the idea is with real time, you can say this would be an interesting place in the sky to look. So what would you do to make this better? Well, the answer is you move it higher. The problem is you sort of have to breathe. Especially old guy, it's nice to breathe. We like that. But the idea would be to build something potentially in the south. Because one of the real future is we'd like to see the galactic center with this technique. And one way you can distinguish dark matter, or better yet, more often you can distinguish not dark matter, is variability. So if you can look at some of these things that people see and you can see variability, you know it isn't dark matter. Because dark matter will not, it's just the density. So if you're looking at astrophysics, you can do that. So building HAWC South is actively under discussion, and potentially building something which could be synergistic to CTA, act as a pointer scope. HAWC cost about $13 million to build. Now, on the scale of things, on a scale of a 200 million euro experiment, it might be good to know when to look at something. And the idea that you could build something for this kind of cost, so then we did discuss it. So the future is probably something in the south, and maybe something at higher altitude, or as one of my colleagues argues, just make it bigger. Bigger you gain gamma hadron rejection, higher and bigger just is what this is all about. So.
Okay, so why don't we thank George again? And I think the way this works is Steel White's joke. Everyone with PhDs gets to go get alcohol.